Modern data centers process massive, continuous IT loads, generating immense thermal output. Extracting this heat efficiently is a massive financial objective for any facility operator. This creates a direct engineering paradox. Aggressive chiller plant optimization systems, or CPOS, are deployed to save money by reducing power consumption. But pushing mechanical equipment to the absolute edge of its performance envelope inherently increases the risk of component failure. This schematic maps the complete MVAC infrastructure. The upper decks house external heat rejection components, like chillers and cooling towers. Below, the internal network manages IT cooling loops for the server racks. Finally, the bottom right houses the CPOS and management systems overseeing the plant. The prime directive of engineering this environment is absolute. We must build a measurable optimization layer to reduce energy consumption, without ever transferring local equipment safety to the software layer. Prioritizing software efficiency over hard-coded physical safety violates Uptime Institute and ASHRAE standards. A software crash must never result in a mechanical meltdown. To enforce that safety boundary, engineers implement a strict command hierarchy. This structure dictates exactly how different systems communicate and rigorously defines which layer holds the authority to override the others. The foundation is the local OEM controller managing physical trips, holding the highest operational authority. The plant PLC above it owns deterministic sequencing. The third layer, CPOS, acts in a supervisory role. Finally, the top layer, human interface, holds the lowest automated authority. Maintaining this hierarchy during a crisis requires specific electrical architecture. If utility power drops, the system relies on a 0-millisecond power write-through, provided by dual-input 24-volt DC UPS loops. These continuous UPS loops guarantee that field sensors and valve actuators never reboot or lose their state while the facility transitions to backup generator power. The architecture establishes a clear boundary. The CPOS is entirely subordinate. It requests efficiency, but the hard-coded PLC strictly dictates the safety and survival of the physical plant. The CPOS optimization engine continuously executes a strict 6-step functional loop. It measures field data, validates quality, estimates load, optimizes plant parameters, applies physical constraints, and verifies the outcome. The validation step is critical. A safe optimizer must instantly reject bad data, such as a frozen sensor reading or out-of-range temperature. It does not average flawed inputs to keep the algorithm running. If a sensor fails, the system immediately triggers a fallback mechanism. It holds the last known good value or reverts to an approved deterministic state, ensuring flawed data is never passed down to the chillers. The physical deployment of this logic is defined by Uptime Institute failure domains, which establish exactly how a plant must survive a component loss. Tier 3 resilience relies on maintainable redundancy. A master and slave PLC pair supervises the plant. If the master goes offline, the slave arbitrates the fault and assumes control, adopting the exact state without contradictory signals. Tier 4 fault tolerance requires strict physical independence, splitting the plant into entirely separate mechanical and control systems, Train A and Train B. With zero cross-train dependencies, a network crash on Train A cannot impair Train B. The distinction defines the facility's classification. Tier 3 survives hardware loss through shared redundancy, while Tier 4 survives through total component isolation. For these optimization algorithms to function accurately over time, they require continuous, unbroken data streams, necessitating edge cache logging at the hardware level. TIA 942C standards require local PLCs to feature non-volatile flash buffers. If the main database link severs, the PLC caches 30 days of sub-second telemetry, allowing the historian to sync the gap and maintain continuous commissioning. With clean data secured, the CPOS deploys algorithms like the differential pressure, or DP reset, to optimize chilled water pump speeds across the distribution floor. The system identifies the most demanding open valve, determines the lowest valid pressure required, and steps down pump speed in small increments. It then waits through a programmed dwell time to verify hydraulic stability. Ignoring that dwell time carries severe mechanical risk. Aggressive software resets cause system hunting, triggering turbulent flow and destroying thermal stability. The ultimate macro optimization tool for a chiller plant is thermal energy storage, or TES, which completely decouples cooling capacity from active compressor operation. During the charging phase, chillers run at high capacity when energy rates are favorable, loading the massive tank with cold supply water from the bottom and establishing a strict thermal boundary. If the utility feed fails, the system discharges. Warm return water flows into the top of the tank, allowing UPS-supported pumps to push the reserved cold water out the bottom, maintaining facility cooling. These algorithms demonstrate that aggressive energy efficiency can coexist with mechanical stability, but only when the physical constraints of the PLC are rigorously respected. The supreme test of this control architecture is a total utility blackout in a Tier 4 facility, where IT servers continue to generate intense heat without grid power. During this event, the automated blackout recovery sequence takes absolute control. All CPOS optimization requests are immediately suspended, so the deterministic PLC logic can manage the crisis. Phase 1 is the ride-through. Direct current UPS loops keep PLCs, sensors, and networks active. Phase 2 assesses generator power, verifying which equipment is available. Phase 3 establishes the heat rejection path, activating cowers and pumps. Finally, Phase 4 executes load stepping, staging chillers sequentially. This load balancing must execute smoothly, without exceeding generator capacity thresholds or tripping breakers. Blackout recovery is a strict safety task. Only after the plant stabilizes can the optimizer be released. Beyond total blackouts, the architecture must also weather edge case failures within the operational technology network, such as loop storms or a severed LAN connection. The control rule for a lost network is absolute. The PLC retains the last validated mode, continues local automatic control, and ignores any stale or delayed remote commands from the CPOS until stable communication is verified. For corrupt sensor inputs, quality logic intervenes. If a test tank probe fails, the system applies range checks, rejects the bad data, and substitutes an approved fallback, like using the maximum valid probe to ensure a warm layer isn't concealed. The highest constraints in the facility are the life safety overrides, protecting against fire, smoke, and ASHRAE 15 refrigerant leaks. National Fire Protection Association standards mandate that physical hardware relays sit directly between the safety dampers and the central fire panel. When triggered, they bypass the software layer entirely, sealing the fluid source valves instantly. Before a facility reaches final handover, the commissioning process demands hard proof of operation. A software command logged in a database is not evidence. The CPOS must reconcile that command against physical RS-485 valve positions to prove the process actually responded. No energy benefit can be claimed without calibrated measurement and a stable baseline. Optimization is only real if the evidence chain remains unbroken from the digital request all the way down to the physical pipe.